Jayant, welcome to the fifth lecture of the subject Signal and System. In this lecture, we introduce the very important concept of even and odd signals. A signal is said to be even if the signal gt is equal to g of minus t, which means to say if we replace t by minus t in any signal, we get the same signal, then we say that the signal is an even signal. So by this way, we mean to say what happens in t positive also happens at t negative, and therefore there will be symmetry across the y-axis. So the signal which is even will have a mirror image about the ordinate axis, which is the y-axis. Similarly, the signals can be odd signals. They can be formulated as odd functions if g of minus t is actually negative times of g of t, or in other words, gt is equal to minus g of minus t. Here, if we replace t by minus t, the signal comes as negative part of itself, and therefore there is basically, you can see, mirror image, but now about the origins, which is not called mirror image. In this case, it is called antisymmetric about the origin. So the signal becomes antisymmetric about the origin. For any given signal, whether it is an even signal or an odd signal or neither even nor odd, we can actually formulate and break the signals into its two parts. One will be the even part and the second one will be the odd part. The even part of the signal can be formulated as given below in this slide. G of et is equal to gt plus g of minus t by 2. So what we can do, we can just take gt, we can take g of minus t, we can add the two and then divide the magnitude by 2, and the resulting signal is the even part of the signal gt. Similarly, for odd part, we can formulate it as g naught of t is equal to gt minus g of minus t by 2. So we take g of minus t, we subtract it from gt and divide it the magnitude by 2 for all values of time, and we get g naught of t. Excuse me. So we can just for one example, we can just directly take. So suppose we have a signal which is k e raised to the power minus 18 ut. You can understand it's neither even nor odd because k it is neither even nor odd. But we can represent this signal in terms of its even and odd components. For that, we require x of minus t. So x of minus t can be quite easily written as k e raised to the power a t u of minus t. And as per the definitions of even and odd signals, we require the summation xt plus x of minus t and the subtraction, so xt minus x of minus t. We can directly write that this xt plus x of minus t can be formulated from above two equations. This comes out to be e raised to the power minus at ut plus e raised to the power at u of minus t. Similarly, xt minus x of minus t, which is required for the odd part, will become k e raised to the power minus at u of t minus e raised to the power at u of minus t. It's very easy. And once we have these, we can directly write the even and odd component. So even component actually can be written as k by 2 e raised to the power minus at u of t plus e raised to the power at u of minus t. Similarly, the odd component shall be written as k by 2 e raised to the power minus at u of t minus e raised to the power at u of minus t, and thus we have the even and odd components of a signal which is neither even nor odd. So in this way we can formulate it. It is also important to visualize this in uh, in the graphical manner. So graphically, the signal can be represented something like this. So it's the decaying exponential, given that a is positive, and multiplication by ut means that only values of time uh, from 0 to infinity are allowed. So this is my signal. What I can do now is formulate x of minus t. So x of minus t is nothing else but the mirrored image of the signal. So now it will be towards minus infinity to time axis. Correct. It's very straightforwardly. We would also require minus of x of minus t because the odd component is basically adding xt with minus of x of minus t. So we can formulate that also. When we take the minus part of x of minus t, it is mirror image about the x-axis, so this also can be very easily formulated. Now based on the our definition, we can directly just combine these two. So we can combine these two parts, right? We can just combine these two parts and divide the amplitude by 2. So this is my part of x of et. But when I am adding it, just pay attention. This is also there in the analytical equation that we have written 3 slides back. At t is equal to 0, actually k by 2 and k by 2 add from both the components, and therefore it is eventually a k. So here it is a discontinuity. The magnitude of the signal here is capital K at t is equal to 0 specifically. To the left and to the right, it remains the same. So there is no problem there. Similarly, when I try to plot these odd components, so you can see I have here what x of t, and here I have what minus of x of minus t. So what I need addition of the two because I've taken minus sign in the signal itself. So I can add it. I can just write it like this. This is the first part, and this is the second part. By the definition of odd, the amplitude will be k by 2 at both the incidents. But again, at t is equal to 0, there is a discontinuity because we are subtracting k by 2 from k by 2. So the resultant is actually, I will write it like this. More specifically, it will be 0 here, and there will be what? Okay, there will be a 0 at the origin, which is also a general observation because 90% of the times at origin it should be 0 if it's an odd signal. So it is an odd part of the signal graphically. We can extend the concepts for discrete time signals as well. The concept remains the same. So if I have xn is equal to un, we know what is xn. Xn is basically a 1 that starts from n is equal to 0 and it continues to be so. It is 0 at minus 1, 0 at minus 2, and so on and so forth. So for nxs. Okay, so in order to formulate uh, even and odd components, I require uh, minus of x of minus n and x of minus n. So x of minus n is very easy. This is my x of n. So x of minus n is just taking a mirror image about the y-axis. So it will be 1 at n is equal to 0. It will be now 1 at n is equal to minus 1. These amplitudes are basically 1, right? And it continues to be so, the minus infinity direction. And it will become 0 at 1. It will become 0 at 2. So this is my n-axis. Similarly, I can just take the inversion of this signal about the x-axis to take minus of x of minus n because x of minus n is this, but we want a negative sign in the amplitude. So at n is equal to 0, you can understand it will be minus 1. Similarly, at minus 1, it will be minus 1. At minus 2, it will be minus 1, and it will go like this towards the negative infinity side. On the positive values of n, since it is n-axis, it will be at n is equal to 1, the value will be 0 because 0 multiplied by minus 1 is 0, and it shall continue to be like that. So now I can formulate the even and odd parts. The even part is addition of the two parts. So in adding, I can write xe of n, which is, remember, xn plus x of minus n divided by 2. and therefore I can add the previous slide. You can see I can just add these two. So n is equal to -1, xn is 0, n is equal to minus n, x of minus n is 1. So I will add, we'll get 1. At n is equal to 1, xn is 1. At n is equal to 1, x of minus n is 0. Therefore 1 plus 0 is 1. At n is equal to 0, x of minus n is also 1, and x of n is also 1. And therefore the 1 plus 1 gives me 2. Divided by 2, it becomes 1. So what I can write, I can just directly write. First of all, give me the values of time. So like this, it will be not 2, it will be 1. So yeah, right, it will be 1, it will be 2, it will be 3, so on and so forth. So this is my n axis. Similarly, it will be -1, and there will be -2, and it continues to go towards minus infinity. At n is equal to 0, I have an amplitude of 1 because we had 1 plus 1 is equal to 2, and divided by 2 it becomes 1, and at all other values the value is half. And this picture also suggests that the signal is even. In fact, we can formulate the odd part as well. So if I want to formulate the odd part, again going back to the slide, I need to add xn with x of minus n. So when I add these two, clearly at n is equal to 0, x of n is 1, x of minus n is -1. So 1 minus 1 becomes 0, by 2 remains 0. At n is equal to 1, xn is 1. At n is equal to 1, minus of x of minus n is basically 0. So it becomes 1, and by the definition of odd component, it will be by 2. So it becomes 1 by 2. Similarly, at x is equal to -1, this xn is 0. However, minus of x of minus n is -1. So I add 0 and -1, I get -1. And then there will be a division by 2 as per the definition. It just becomes so simple. At 0, the signal is 0. At 1, the signal is positive half. And at -1, the signal is negative half, right? It continues to be like this. And by the look of it, it is anti-symmetric towards the about the origin, and therefore this is the odd component of the signal, very well justified. Correct? There is also one another way in which we can represent the discrete time signal. It's using curly braces. In middle of the curly braces, we can just take a point an arrow, and this arrow actually suggests that this is the point at n is equal to 0. So this is a signal which is discrete time. These are the values now. If the arrow gives me n is equal to 1, therefore at n is equal to 0. So therefore at n is equal to 1, the value of the signal is -4. At n is equal to -1, the value of the signal is 1, and I can just go like that. And we can formulate the even and odd components using the same formulation, and it is up to you to verify. It is a very like I can write what x of minus n as using the same. So at the 0 point remains the same because it is the pivot point. So at n is equal to 0, we have a 2. Basically what was at n is equal to -1 will become at n is equal to 1. Similarly, what was at n is equal to -2 will become at n is equal to 2. And now in this direction, similarly at n is equal to 1, xn is -4, so it will become -4 at n is equal to -1, and it will become 2. So I can just directly write xe of n, which is what? Addition of these two point by point, xn plus x of minus n by 2. So I can directly write this -3 plus 2. So it becomes -1 by 2. Similarly, 1 minus 4 is -3, and definition gives me -3 by 2. At 0, it is basically 2 plus 2 is 4 by 2 is remains to 2. So it is my value. At n is equal to 1, it is basically -4 plus 1, which gives me -3, and by the definition there will be a 2 in the denominator. Similarly, I can verify that there will be -1 by 2 here. Correct? So this is my even component. We can also formulate the odd component similarly. And by formulating the odd component, it is just subtracting this from this. So minus 3 minus 2 will give me what? Minus 5. So it will be minus 5 by 2. Similarly, 1 minus minus 4, which becomes 5 by 2. At 0, it is 2 minus 2, which is 0. And it will be, if it's an odd component, it will be something like this. It will be minus 4. Okay, it will be minus and it will be plus. It will be minus and 2 plus. Now it is correct, I think. Because at n is equal to 1, this xn is minus 4. So minus 4 minus 1 is minus 5 and by 2 by the definition. So we can also represent discrete time signal in curly braces as arrays. And this was the point to give an indication. Just quickly, one more important aspect, that is performing some operations on the independent variable. The independent variable in all the signals is basically time axis t. So we can perform 3 operations. The 3 operations are shifting, scaling, and reversal. So the first operation is shifting. Shifting you can quite easily understand. So if I have a signal like this, just an arbitrary signal xt, right, with respect to t, I can perform, suppose this is just for illustration purpose, this is this is plus 1 and this is minus 1, right? The amplitude is, say, a, so it remains a. So if I plot x of t plus 1, it is to write, it is basically x of t minus minus 1, right? It is to write like this, and therefore I can just this is basically the signal now which is acting at t is equal to minus 1. So right now the original signal is acting at, the origin is at t is equal to 0. That origin now shifts to minus 1. So it will be a signal like this. It will shift leftwards by 1 unit, and the signal is called advanced. The signal is called advanced version. So what I can do, I can just like this. So the plus 1 point will come at 0. The center point, which was 0, will become minus 1 and it will be minus 2. Amplitude remains a. Similarly, we can formulate what will be x of t minus 1. So this will be now acting at t is equal to 1. This point which was minus 1 will come at 0. The point which was plus 1 will come at 2. It will be right shifted by unit 1, and signal is set to be the delayed version of the original signal. So when it is x t plus 1, it is at minus 1. At t minus 1, it becomes at 1, correct? So we can just write that in general. I can just write that it is basically what, x of t minus t naught. If t naught is positive, we go right. If t naught is negative, we move to the left. It's just thumb rule, so to say. Second one is the scaling. The scaling is a factor which is, if I have a signal xt, I can formulate. So suppose, again I will take the same signal just to introduce the concept. So 1 minus 1 and a. So I can write like x of t by 2. So in general, if I have x of at, just divide the t axis by a. That's the thumb rule. So it is 1 by 2 right now. So what is the value of a here? The value of a is 1 by 2. So I will divide time axis by 1 by 2, which means I will multiply the time axis by 2. So I can just take the time axis, the same signal, So what was at -1 will now become at -2. What was at +1 will become at 2, and this will be my signal. Uh, there will not be any change in the amplitude. Basically, I can also draw what is x of 2t. X of 2t. So x of 2t is basically dividing the time axis by 2. So what was at -1 will become now at -1 by 2. Similarly, what was at +1 will become at 1 by 2. Signal remains the same. The amplitude also remains the same, right? It's just that we have scaled the signal. That's about it. We have just scaled the signal. Third operation, which is very easy, it is reversal that we have seen so many times now. So for this, if I have an xt, just take any example where we can find that there is a reversal. So suppose the amplitude is a, it is -1, this is +1, this is my x of t. So I can directly replace t by -t, which is to say I will take a mirror image across the y-axis. So what was here will come here, what was here will come here. So the point 1 will become what? -1. The point -1 will become 1. And similarly the signal will take just a mirror image about the y-axis, something like this. Now quickly, what are the sequence of operations? The first operation that I will always suggest to do is shifting. Always perform the shifting first, then we can perform scaling, and finally we can perform time reversal. Remember what we are talking about here is the transformation or operation on the independent variable, which is the time variable. So the time variable is the one that we are looking for, not the amplitude. So in amplitude there is no operation for which we are discussing here. So the shifting is corresponding to time axis, the scaling is corresponding to time axis, the reversal is corresponding to time axis. Just for an illustration, we'll take the signal xt. I want to plot this part. I want to plot x of -2t plus 1. So first operation is shifting. So I will neglect everything. I will just write x of t plus 1 and x of t plus 1. So suppose for our convenience I take it -2. Okay. So for this signal, x of t plus 1 means what? All the points will shift towards the left by 1. So the 2 point will come at 1. The -2 point will come at -3. The 0 point, which is the center point, will come at 1. Correct. So now you can just clearly look at the signal. In our case, it is having an amplitude at 0, so it will amplitude of 2, so it will take a amplitude of 2. It will come like this and then become join the x-axis, and here at -2 it was of amplitude 1. It continues to be amplitude 1 till t is equal to 1. So this is my signal, which is x of t plus 1. No issues whatsoever. So this is 1, this is 2, and straightforward. Now the second operation that I have suggested is scaling. So we'll do scaling. Scaling is x of 2t plus 1. So understand what I'm saying is that in this signal I will perform a scaling now, which means I will divide the time axis by 2, because here the value of a is 2. So -3 point will become -1.5. One value will become 1 by 2. Again, one value becomes 1 by 2. Correct. So it will be something like this. The amplitude remains the same. We are not altering the amplitude. Correct. It will be something like this. Something like this. So this is my x of 2t plus 1. Now the final what is required is x of -2t plus 1, which means now I will perform the operation of reversal. So we'll take all the points in time and we'll make them minus types. So -3 by 2 becomes 3 by 2. minus 1 by 2 becomes, basically this was minus 1 by 2, so minus 1 by 2 becomes 1 by 2, and 1 by 2 becomes minus 1 by 2. So it will take just the reversal, so it is having a magnitude of 1 from 3 minus 3 by 2, so it will become from 3 by 2 it will become 1. It will increase like this to 2 and will again jump back uh, to 0. So it is basically 2, this amplitude is 1, this axis is time. So you can see what are the sequences, right? So the sequence is very simple. It is shifting, then scaling, irrespective of the equation. These are the operations, and then finally reversal. Understand that all that has been said here also applies to the concept of discrete time variables as well. So this is for this complete lecture, and from this lecture we have introduced the concepts of even and odd signals, and we have introduced the concept of performing operation on the independent variable. The independent variable is generally in signals to time, so we perform some operations on the variable time, and we can use the operations shift, scale, and reversal in these sequences, as I said. So shifting will be done first, then scaling, then reversal. So this is all for this lecture. Thank you.